And then hello, everyone.
Hello.
Courtney, how are you?
Courtney, I think you got muted.
Oh, no. Oh, Courtney is muted.
It won't let me unmute.
While Courtney gets that all straightened away, welcome to an Automation Ladies podcast episode with a good friend, Ted Weerts from MX Interface. And then, of course, you have Courtney Fernandez from Automation Ladies, and then me. This is my first time on the Automation Ladies podcast as a host, or co-host, rather. So, Courtney, did you get your sound fixed?
I think so.
Yay, we can hear you.
I think it's actually my internet being kind of a jerk right now.
Oh, so Albert.
If I go a little bit max headroomy. Don't blame the IT guy. Yeah, it might be my laptop just choking right now. Because that's what he's whispering in my ear. But anyway.
Game time.
Yeah, well, it's like once you go live, everything decides to die.
Yep. Well, thanks for having me on. I'm excited to show you guys what we've been working on. Yeah, looking forward to share it with the world.
Yeah, I think what your product is really cool. And I apologize for not remembering the original interaction we had, but we've crossed paths in an advanced training at UR before. And so I understand like the UR side of life pretty well on most applications, just because I spent so much time like actually doing applications with them. But I actually had like a lot more fun, in all sincerity, like not to say that playing with robots isn't fun, but I had more fun interacting with people and, you know, getting to show people who have, you know, either never used a robot before in their life, how to use a robot, or show other people that, you know, have used traditional robots longer than I've been alive, you know, telling me things about robotics. So I always really enjoyed that. And then, you know, these relationships always kind of resurface later on. And this is a really cool full circle one, because I believe you and Emily found each other actually. And how did that come about again? Because Emily, what you do is honestly pretty cool for our industry.
Yeah. I think just me talking about like Automation Ladies and OT Skatacon and kind of my role in marketing with that led him to reach out to me, right?
Yeah, that's right. I was seeing the Automation Ladies posts on LinkedIn and drilled down from there and ended up meeting Emily, and we've been developing the brand from there. So I've been watching Automation Ladies and some of the posts and podcasts for a little while. I have pulled up some of the shorter episodes in the car while driving before too. It's nice to hear from the variety of people in the industry with different experiences and different applications than myself.
I actually don't listen to my own episodes. I don't know if you guys have ever heard Nikki talk about that too, where like we just don't want to hear ourselves.
Yeah.
But I'll pull up episodes where it was just her talking, you know, or to a guest. But I've considered a few times, like maybe I should go back and listen to some of the old ones that I was on.
It's kind of like a musician listen to their own music, you know?
Yeah. Actually, I mean, I don't play anything, but I can imagine, like at one point I did like sing for a little bit in a choir, and I hate hearing myself sing, and I hate hearing myself talk. So
Yep.
Hey, but you're good at it. You're a rock star at it at OT Skatacon. You second year in a row where you had one of the most liked sessions. So there you go.
Thank you. I think people just like robots, honestly. I'm just
they're exciting.
I got the topic, you know, that people want to hear about, and you know, like AI and stuff are very AI and robotics and what was the other thing I was going to bring up? But there's like 3 really hot buzzwords right now. I think that if you speak on it, you're like automatically going to get a lot.
Cybersecurity.
Yeah.
Cybersec. Yeah. I think that's it.
Well, on that note, do we want to talk about why we're here today?
Heck yeah. So we have, I have seen a number of customers that have like the full range of like not automated at all, up to like fully automated machine shops.
Right.
And I think the machine shops that are somewhere in the middle are in an interesting position. Some of them are just starting to put robots in front of machines and see, how they can help. And the increase in, quality and or throughput or adding another shift. But like, there's like a lot of benefits that they're seeing that maybe they didn't know were there. And then also they want to scale up, but this is becoming like a not a headache, but, trying to see the future with more robots and now suddenly a whole bunch more actionable data. Where does it go? How do you use it? Everybody says AI, data-driven decisions. What does that mean to me when I have chips of metal everywhere? What does that mean specifically for me? And I think what your product offers is unique in that, like, it's a fleet management. Correct me if I'm wrong, but it's not just for mobile robots. It's for your entire technical fleet, so to speak, including your stationary robots. Like,
absolutely.
So instead of me trying to explain it, why don't you explain your product? Because I think it's I think it's very unique.
Yeah, absolutely. Well, first I'll start with myself. My name is Ted. I am the founder and principal of Process Robotics, and we have been developing what is our flagship product called MX Interface. So we've been developing robotic solutions for some time now, offering integration services for a variety of applications. That might be turnkey cell design, mostly around machine tending, but we focus on multiple machines, many machine tending. We fill in the business with specific applications. We've done assembly applications. We've done some logistics applications, but a lot of our business comes from machine tending applications. I've got, let me pull up a couple slides here.
Please do.
Yeah.
We love visual aids.
Give me 1 second to
show us the fun stuff.
Yeah. So we have been in business for a little while now, installed several robots. We've probably got nearing 20 robots now that we've been involved in. I was previously employed with a manufacturer, and my role was to develop and deploy the robots into this facility. This was new to the company at the time. So like you were describing, Courtney, it's this kind of middle scale manufacturer. They weren't a job shop. They did have a commercial product, but CNC was their largest manufacturing technology by far. Nonetheless, they were in between this small scale business and these mega scale businesses. Traditionally had just used human labor to do nearly everything. So I was tasked with studying, learning about the robots, figuring out how to deploy them into the business, how it fits into the business, and how to operate that in the facility. The business itself has been around for a little while. We have serviced several local companies here. These are all local to us, but we've got robots at all of these component manufacturers. Warren is an exciting one. I've got a little video that we'll come to in a little bit of actually MX Interface, our product, running real production and making real parts. We'll take a look at that in a little bit. Courtney, tell me a little bit about where some of this might fit. In our experience, we see robots get deployed often in a one-to-one scenario where one robot is tending one machine. That's all well and good, but the reality is that robot has a lot more capacity to give. It's very easy and apparent to see that the robot sits still for the whole machine cycle, right? It's sitting there doing nothing. You've done several cobot applications. What does this, where does this fit in the larger scheme of things in your experience?
In my experience, what you said is pretty correct. It's like a one-to-one type deal where you'll put one cobot in front of one machine, and that's its life. And from what I have seen and I've heard a couple of times, is the average CNC cycle time is like 7-8 minutes. So there's a bunch of minutes that the robot's sitting there doing nothing, and then it does an operation for 1 to 2 minutes and then goes back to sitting still for 8 minutes. So a couple of folks have gotten creative, with repositioning machines and getting them closer. But that's not always like if you can position a robot so that it can feed multiple machines, or tend rather multiple machines. You have like one program per machine that you'll switch recipes really quick to get something over from that. Like say you have to do a tool change, or you have dual tools and you got to switch TCPs. But it's like either one monster robot program that's becomes unwieldy and hard to open and all kinds of other problems, or you just have multiple robot programs, but you got to switch between the robot programs whenever you switch machines.
Yeah, and that's not to mention the physical connection of those, right? I mean, it gets exceedingly complex the more devices we want that robot to interact with. When you go from, I mean, you're doubling it, tripling it when you talk about going from one machine to 2 machines to 3 machines, and as you just mentioned, the logical flow within your program, so that the wiring gets more complex, and then the logical flow inside your program gets even more complex too. And that's a lot of things to manage. There's a lot of moving pieces there. And we think that's what MX Interface can help address. So I'll move back to a couple slides here, if Emily can pull that up for us. So when we talk about going from one robot tending multiple machines, that makes the problem space a lot more complex. We've got a specific integration with each machine. Traditionally and classically, this might have been a bundle of copper wires. Today, that might be a field bus cable or something, Ethernet or something a little bit more advanced. But nonetheless, you're dealing with 3 discrete or 4 or 5 or however many machines, 2 machines, whatever that is. There's that many integrations. We literally have to handshake the robot with that many machines. So what we've been building is MX Interface. What we want to develop is a smooth interface layer so that all these devices are only having to interact with one device, if you will, one component in this whole ecosystem. What this does is makes the interface common across all of them. So now all of a sudden, this robot doesn't have to know how to interface and interact with 3 different logics that might be presented differently. It can interface with MX Interface, and on the opposite side, those machines are interfacing with MX Interface, again, in a common pattern. What this does is it makes it extremely scalable. So now all of a sudden, because we have one common interface, it's much simpler to scale our fleet. We can add another robot. It's the same logic. The robot's going to talk to MX Interface, and MX Interface is going to deal with multiplexing and handling what was a rat's nest of wires. So when we talk about machine tending at scale, we've been sort of setting the stage here for the complexities involved. It gets more complex and more difficult the higher up, the larger the scale goes. Which robots are not already busy? Which robots have enough battery capacity? How do we monitor success and failures for that matter? How do we recover from failures for that matter? If we, in the traditional sense, if we had integrated all these robots with all these machines, that may be that many different failure recoveries. There may be different failure recoveries for different pieces of equipment. There may be different interfaces for different pieces of equipment. So we'd have to build that many interfaces. It might seem simple on the top. The machine says it's complete. We send a robot over there. We could just pick a random one from the pile, but there may be some challenges to that, something in the way. One of those robots might have a fault. One might be charging. One might already be busy. From there, we've whittled that down a little bit. But finally, we need to actually task one of these robots to do something. So MX Interface creates an environment for many devices to publish their state. It does this with MT Connect. So all of these devices on a foundational level are publishing their state to MT Connect, which is a common language and vocabulary. We'll take a look at that in a little bit. To describe the flow here a little bit, a machine will signal that it's complete, and MX Interface will dynamically generate tasks in response to those machines. So a machine says that it needs to be unloaded. MX Interface recognizes that and will generate a task and post it on something of a job board, if you will. It will optimally allocate those tasks to robots. How we want to do that is controllable. Is that the robot with the highest battery capacity left? Is that the robot that's the closest? Is that the robot that will yield the fastest outcome or the highest production? All of those decisions and how we want to optimize that is controllable within MX Interface. To actually make something happen, we can bind a specific robot to a specific task and send it to execute that task. It will automatically transfer those task-specific programs that you were talking about. That might be specific to machine. One machine might be a little different than another. And then finally, we monitor those tasks for success, or that maybe a even more practical reason is failure. We want to know if the robot failed to get that part in there correctly. So we can recover from those tasks, and we can actually unwind those tasks too. So we should be able to we need the capability to be able to unwind that. If we're really going to take our hands off and automate production, we need to be able to, we need the system to be able to unwind a failure and kind of go back from that and recover. Yeah. So as I mentioned before, it's MX Interface is built on MT Connect, and the actual device-to-device data flow is pushed through MT Connect. This is a little bit of a departure from the common automation integration, where we might have read and write capability back and forth between devices. Traditionally, we might, in a simple example, we might put a copper wire from a digital output on one device to a digital input on another. We can kind of read and write back and forth. MT Connect separates that so that all devices are representing their own states. They're all, and they can write to themselves. Each device can obviously manipulate its own data stores, but it behaves in response to other machines on the MX interface. MT Connect is a interoperable semantic vocabulary, and it provides structured data that's not proprietary to any brand. For businesses, this leads to more efficient operations and improved productivity. They can really focus on their special sauce, their process, their parts, their production process, and not have to worry about the intricacies of getting specific data out of devices. So MX Interface connects robots to multiple machines, making it easy to get the most out of your equipment. And there's a typo there, but it makes it easy to get the most out of your equipment. That raises a question, though. And the question is, how many there's two questions. How many machines do we need to meet production? And how many robots are needed to sustain those machines with minimal downtime? So this is where we've got a little tool here. I'll leave this up if anybody's on the computer and wants to follow along. In a moment, we will switch over to our website and take a look at this tool in detail. We have a tool on our website that will estimate capacity for your production based on the cycle time and expected number of machines and robots. And Courtney, I see you scanning. If anybody's on the computer too, this is, of course, is a hyperlink for me, but you can type in mxinterface.com and scroll down below. I think it's the third section down, and you can. This tool is available and free to use. You can check it out, and I hope that it's useful for you. What this tool will help uncover is two things. One is the interplay between one robot tending one or multiple robots tending multiple machines, and potentially uncovering hidden capacity within our robots. I think that a lot of robots get deployed into applications and they fill the need, but that robot is underutilized. There's a lot more capacity that can be leveraged in that robot, especially in machine tending applications. So I will go over there now. I've got it up. Oh, I'm on the other window. Okay. So here's our website. If you just scroll down a little bit, there's the capacity estimator down here. And let's come up with a scenario, Courtney. So I don't know. We were talking earlier about typical cycle times. What does that mean to you? We were talking about, what'd you say, like 7 minutes, 8 minutes?
Yeah.
So let's just say we've got
400 some odd. Yeah.
Yeah. Say our cycle time is 480 seconds. That's very reasonable. 105 seconds as it defaults here would be an exceedingly fast cycle time. That'd be a drill and tap or something quick.
Great
but
place
let's
to put a robot.
yeah. So let's put some real numbers in here. Let's say our cycle time is 480 seconds. With one robot, if it's static, a 30-second handling time is probably pretty quick. Might be attainable if the robot's literally just sitting outside those machines waiting for right at the door. What we can immediately see here is that right off the bat, I can tell that these robots, have overhead capacity that's not being used. These machines are going to produce parts at, 113 parts every 8 hours, or 14 cycles, an hour. Our robots have a ton of extra capacity here. The robots have 8.5 times the load unload capacity as then is required to run these machines. That robot's underutilized. We could utilize that robot much. We could have that robot interface with multiple more machines to get a little bit more utilization out of that robot. At the same time, we're going to get more output out of our whole facility. So even at this high cycle time, this robot can start tending, upwards of 10. Now, there's some reality problems here. Machines are big. Robot reach becomes a problem. If we really start talking about this many machines, we need to start thinking about how that robot moves from, can reach all of those machines. You've seen seventh axis before, but another way to approach this might be mobile robots. And that's where we're going, and that's where we want to get to. We want to see mobile robots being able to drive around and tend a lot of machines. We see that they have a lot more capacity.
Handling time would also include like robots ETA, more or
Correct.
less. From
Correct. So if we start talking about 4 machines, for example, machines are big. Now, all of a sudden, we're going to either need to put that robot on a 7th axis or mobile robot. And as you pointed out, that's probably going to take a little bit more time. So that's going to eat into our robot capacity here a little bit. But 4 machines on a 7th axis, let's just say that it's going to take a total of 60 seconds to slide down the rail and do its business. So we can update that here, and we can see that we're starting to make a little bit more use out of this robot. Now, we still have some overhead capacity, and that's coming from this long cycle time.
Right.
Ultimately, the math in the background ends up being the important ratio is the ratio of cycle time to robot handling time. Once those get really close, that's when you're going to need a lot more robots to tend this. We're going to have a big problem if the cycle time is close to the robot handling time. It's almost inevitable that a machine's going to wait for some time. The solution to that is, of course, that we can add more robots to that scenario. Yeah. So the solution to that is that we can add more robots to that scenario.
You have to probably go mobile because multiple robots on a 7th axis gets
exactly
tricky. You can't, hop over each other and.
Absolutely. I mean, yeah, and that math would get even. The math gets pretty complicated there if one's in the way and you got to block, and that you can't. There's a robot on one end and it can't get to the machine on the other end. We've certainly made some assumptions with this tool. The biggest one is that everything's sort of frictionless. There's no challenge, there's no hurdles or anything for a robot to get to a machine. And I'm sure a lot of viewers right now know that the reality in a manufacturing environment is that there's going to be some challenges. There's going to be chips on the floor. There's going to be, a slow machine door or a broken tool or things like that. Hard to account for.
If you're any kind of gamer, it's either going to be Frogger or it's going to be Final Fantasy Tactics.
That's right.
If you got that joke, mention yourself in the comments as a mega nerd.
I do want to point out, if anybody's using this tool, that we do have another variant of the same tool where we can estimate the number of machines, the minimum number of machines required to produce a certain quantity. If we have our same example over there of 480-second cycle time, and I don't know, let's just say, for example, we needed to make 500 of these parts, and we want to do it in 8 hours. In theory, we could do that here with one robot. We'd need 10 machines, which starts to get a little bit large. So we're probably talking about mobile robots. At best, we're talking about a 7th axis. We're still 10 machines starts to be a big sell, though. So this tool's free and available to use. I hope that it's useful. We hope that people can recognize that there's hidden capacity in your robots, and that we can help them interface one or multiple robots with multiple machines.
I actually really like how you broke this tool down, because the tool in and of itself is pretty useful. If you're just gonna, if you're a machine shop thinking about making a change, you can kind of simulate some things here, or simulate some data here. But like you've explained kind of what these two, ramps mean and what it looks like when you have capacity. So like you're giving some meaning to these numbers. I think this is a very useful tool, honestly. I don't know. Is this fairly new? Because I went to your website.
Yes.
I don't remember seeing this.
Yeah, it's very new.
I like it a lot.
Thank you.
I love it a lot too from a marketing aspect. This makes my job way easier. So love it.
One way you might end up, I see someone might end up using this, is that you may flip back and forth, right? You might use the machines tool to get an estimate number, but maybe that's a really large cell, and that might sound that might be daunting for multiple reasons, facility layout reasons, just complexity of number of pieces, number of parts. So you might use both versions of the tool to go back and forth. Maybe we could experiment with cutting this in half, right? Maybe we could experiment with, okay, well, what happens? This is we need 10 machines, but maybe we should conceptualize and think about 2 work cells with 5 machines each. And what will it take to get there? And maybe we can get that same 500 output out of 4 machines Almost. We can't quite get there. It does look like we will need all 10 of those machines, but we could cut that in half, right? We could say that the instead of 10 machines, we could shoot for 5 machines, 2 cells of 5 machines. So there may be usefulness in going back and forth between the two. The one with the sliders is kind of fun. You can kind of slide the things around and see everything change. So that's sort of fun to use, but it might be useful if you get a minimum number from the machine side of things and then come back over to the output side and sort of play the what if game up and down.
Yeah. And you could play with multiple factors, which is,
Yeah.
I can write an Excel spreadsheet that does this probably, but I am bad at UI. And I think a lot of us actually are probably bad at UI. And this is very simple and easy to understand UI.
and maybe it's this could be useful just for planning purposes, right? It's like, well, quickly calculate how many machines do I need to make X parts in a time. I'm going to need to dedicate these. Of course, it's an estimate, so paint it with a factor of safety, but this will get you pretty close to the required machines. If anybody's out there using this, we have found that the most optimal place to be, one robot can usually handle about 3 to 4 machines. In this case, well, we've got an exceedingly short cycle time here, but of course, dynamics and the cycle time and the robot handling time matters, but as a broad watercolor paintbrush, one robot can typically tend about 3 machines. Typically in most, the kind of average cycle times, you're going to see that we'll be able to tend about 3 to 4 machines with one robot. Even more when we talk about many machines, that's where we're going to have to start scaling up multiple robots to meet that capacity, to maintain that output.
So what's the most complicated example that you've seen implemented using this tool?
Well, we're working on mobile robots. So that's certainly that adds the complexity that the robot's got to move, right? I mean, there's a lot more mechanics to it. But aside from the complexity within, like inside the mobile robot, just handling many machines and knowing when to approach each machine from the robot's perspective now, it gets difficult. And further, how do we keep track of that, right? My very first robot install, the second iteration of my very first robot install was actually 2 machines, 1 robot, and learning how to keep track of that other machine that just finished while it was currently busy was, we got through it, we figured it out eventually, but that is a complexity, and that's only 2 machines. Now you start talking about 4 or 5 machines. We need to keep track of those requests. Yeah, liminally spacious. That's correct. You can. I'll be the CEO of Skynet. Actually, that'd probably be a robot. I would probably be a pedestrian there.
Think of what we can keep. We just got to keep them occupied with something, that they think is destructive, and
yeah, that's
program them to just waste their time.
That's right. Yeah,
that's how we defeat AI. Just make it go waste its time.
Let me get back over here. Yeah, so please use the tool. All of the viewers out there, let us know how it works for you. We'd love to hear your feedback too. If there's something that you would like to see out of the tool, let us know. We'd love to add that. Off the bat, Courtney, anything that you can think of, any sort of metric that would be useful to gauge robot and machine capacity and for planning purposes, anything immediate that comes to mind?
I mean, I think you pretty much nailed it with your intended cycle time, and basically the maximum speed you want to make that robot go.
Right.
Because that's like another factor is if you're machine tending and you're a robot by yourself, or you're on a 7th axis and you've just pulled out like a freshly cut piece of aluminum, you probably don't want to be wielding that thing around super fast. And I imagine the risk assessment for that would be a lot of fun to do once we start doing like 7th axes and mobile robots going around holding sharp things, that we've just pulled out of a machine.
Yeah, so it's kind of funny, the term cobot, and the of course now there's popular news that's changing, and we're trying to walk back, the inherent
the perceived, the application, not the robot arm.
Yeah,
right?
The perceived
we were
softness.
Just saying, a robot with a machete is
that's right.
Not necessarily collaborative.
Yeah, right. The arm is very smooth, has this very sleek design. It seems very soft, and it's not going to harm anything until you put the sharp. Companies around here like Benchmade and Leatherman, they're literally pulling out knife blades. So, go figure.
Again, would love to be involved in the risk assessment. Snappy D bot.
I mean, I think it just means a cage.
Yeah,
it's probably the quickest.
The only solution, really.
Yeah.
I'd be curious about how creative people could get and still not use a cage. I would just cage that thing.
Yeah.
And then if you got, do you have situations with AMRs and cobots, or AMRs and arms, carrying around sharp pieces, and at that point, are they typically, walled off from the rest of the world? Is it, this is a no human area everywhere the AMR is allowed to go?
My approach to that would be to set the sharp piece down on top of the AMR and not have it in the robot arm while it's moving. I'd rather have it on, in a bin on top of the mobile robot just laying there, than it in the arm during transit. The mobile robots we've used, the enabled robotics platforms, I don't believe that the arm would move while the base is moving. So there's that. But of course, I don't know, you could probably figure out some clever way to get arm motion out of it while it's moving. I don't know if that'd be desirable, but you could make something as dangerous as you'd like.
Yes. And I'm honestly, as you're talking, I'm thinking my way through like, well, you would put it in a fixture and then regrip it, but then you got to add the time for grip and regrip on that. It gets to be a complicated problem to solve very fast.
Right. Frank's got a question here. How does the cost of MX interface compare with a master PLC station controlling robot allocation networked with the production machines? Also, have you had applications with tool changes? We have very limited exposure to tool changes, but our vision for the mobile robots is that the process specific things that are running for that specific job at that specific machine would stay at the machine. And what I mean by that is that the raw material for that work order and the gripper associated with that shape part would be stationed at that machine. Our vision is that these robots are driving around the facility with no gripper on the arm. They have the arm side of the tool changer. That's right. And they will drive up to the machine, pick up the gripper relevant to that job, because the job is an instance of some work being done at a location, and that location is the machine. To address Frank's first question here, it's significantly reduced. For one, we don't even have the PLC involved, so the PLC hardware is not even involved. We'll talk a little bit when I get to the. We've got an Isaac Sim demo coming up here in a little bit, but I'll talk about it when we get there. We have a IPC that is connected to each device. So every device gets a small IPC near it, and that's running our MX interface logic. That's that smooth interface layer that we were talking about here. Shrinks all of that logic costs that we would associate to a PLC and all of the complex program we were talking about before, and it compresses it all into MX interface in the center here. So we've eliminated the PLC itself. We've eliminated a lot of I/O wiring, a lot of discrete I/O wiring. And we've reduced that down to just Ethernet cables between the device and its respective IPC.
So how powerful an IPC is really needed for this? Can I just go crazy cheap as long as it can? Like,
Probably. In the lab here, we run a bunch of Raspberry Pis. We run them on Raspberry Pis. We have run, let's see, the cell that we have running at Warren Industries is running three adapters, we call them. That's the jargon for the little software component inside MX interface. There's one adapter per device. We're running 3 of those on one Raspberry Pi device. You probably see some saturation around 4 or 5 devices. But frankly, at that price, we could just spread that out across a few more devices and buy a little bit of overhead.
Right.
So it's very lightweight. And our software will run anywhere Linux runs. We provide a complete solution to our customers, so they don't need to source their own hardware. But we can work with larger scale deployments with specialty hardware or help, guide that selection along. So to answer, it's pretty lightweight. It's extremely lightweight. MT Connect is all REST based. So it's anywhere that we can make those calls over the network. We're good to go. So we can move into a little demo here. I've got an exciting Isaac Sim simulation that is running our actual MX interface software. To set the stage for that a little bit, I just want to talk a little bit about how this demo was set up. So the demo we'll see in a moment here has 1 robot on a 7th axis, and there's 3 machines involved. Those are all interfacing with MX interface by way of ROS2, and we're seeing that out through Isaac Sim. Isaac Sim in this case is Isaac Sim and ROS2 combination is in a simple sense, it's a viewer for the logic that MX interface is running. We could run that MX interface kind of at the terminal level. Thanks, Ben, and we'll get there in a second. MX interface would run at the terminal level. Of course, that's not very exciting. We all want to see the robots move around in the real world. We want to see it load real parts. But Isaac Sim provides a mechanism for us to be able to see that and witness that. So let me switch over here and shrink all of my windows. Oh, I was doing the other window. Okay. Sorry, let me switch windows here. All right. So, oh, that's not there we go. So this is our scene here. I've got a little bit of a backdrop, but we can see that there's 3 machines and a robot on a rail. The rail's a little crude. I just figured that for fidelity purposes, that was, that'll suffice for now.
Yeah.
And this also brings us to the introduction of our web app. On the left, you can see Isaac Sim. That's our shop floor. On the right is our web app. And actually, let's just go and we can manage users. So we can control access this way. You can add operators. You could share a login if you needed to. We can defeat that login too if that's just not a concern. Starting with device management, we can register new devices into the MX interface platform. We'll walk through that here in a moment. But I've already got this cell signed up and everything's registered here. We've got 3 machines, 1 robot. We could go through this and we could add another robot, for example. This won't be represented in the Isaac Sim simulation. That would require adding that to the scene, but I'll just walk through adding another device to MX interface here. We could add a second robot, our little naming pattern with MXI that we use for UUIDs. That's just a unique identifier there. For device type, we currently support Haas and Fanuc CNC machines, and UR and enabled robotics robots. We're always adding new robots, new machines to this. If you don't see yours here, but tell us, let us know. The device host, would be the IP address. I don't know, I'll make something up here. And the device's port, so we can pretty quickly configure and add a new device. Let's just say that this robot has a door interface, meaning that on the robot side, it's able to request doors to be opened and closed. On the machine side, it would be able to respond to door open and close requests. For this example, let's just say that this robot doesn't have a chuck interface, but that can be enabled here too. There's a few more configuration here. This is a little bit more advanced, but let's just advance through this. We can configure I/O. Currently, we don't support that through the web app, but we can help customers configure that, and that's configured with some simple text files. So we can save this device, and that's cool. Oh, genius. Well, at least that works. Hey, look, it caught the, that wasn't a properly formatted IP address. The message there was a little bit, oh, and that ID already exists apparently. Oh, sure enough. Hey, look at that. It even does error checking for us. So here's our new device. This has just been added to the MX interface system. Over in, we can finally see those devices here. That device we just added is not shown here because I don't have an adapter running for that device. I set this up in advance. In a moment, once I start all of this, we will be able to see the tasks come across here. Those will be load and unload tasks, so we'll get that started here. We can see a little bit of detail about this machine on the side as we click it. Just some info and some specs about the machine. So what's important to note here is that this MX interface is really running in the background here. These adapters are running. So we've got, I've got a couple of them running here. Those are on Raspberry Pis behind me. But those are actually running and communicating with Isaac Sim over ROS2. So let's go ahead and fire this thing up. So we just started these 3 machines, and they started requesting tasks. So what we're seeing here is each machine is requesting to be loaded. So there's material load for machine 1, 2, and 3. And this third machine was, you just saw that task was preparing, and then it moved to committed. In a moment, machine 1, and we can actually see some actual motion there. There's some really crude G code running there, not really that advanced of simulation, but at least the table's moving around. So we can see those tasks as they come up. Another task for machine 2, load just came up, and it's preparing, meaning that there's no bound collaborator yet. There's no robot assigned to it yet. But we can see those tasks come up and bind to the robot. This is the magic of where we can keep track of those requests. A few moments ago, I was talking about the complexity of a machine across the facility finishing its business and needing to be unloaded. In a simple fashion, a digital I/O might miss that without the appropriate logic. We need to store that in some sort of durable storage so that it can be picked up later. But this will go about its business, and the robot will slide back and forth, loading and unloading machines.
And you can see the status is updating in real time. That's really cool.
Yeah, and we'll see these are all previous tasks, so they're marked as complete, and then they're marked as removed. They get removed from the MT Connect agent as they get completed. So we don't need to worry about them being, hung up or caught up on anything. But along that same vein, we can start to see when something does get hung up, right? Maybe one of these machines from this dashboard, we could see, hey, this task was last updated, 3 hours ago, and it's sitting at preparing. Why hasn't it gotten the robot? That could give us an indication that there's an issue with the machine, maybe an issue with the robot, that's keeping it from executing that task.
Wow. I mean, I'm blown away.
Well, thank you. I
hadn't seen this yet, so this is
yeah, this MX interface is running.
There's something very powerful about seeing,
for sure,
visual, like things happening.
Yeah.
We used to do simulations with, like have a customer send their part, like the CAD for the part, and just show a quick motion with their part in it. But there's something very powerful about seeing like a robot handling your part or seeing a robot doing your process in front of you.
Right.
That just adds a layer of confidence to what you think you're going to do.
Yeah, absolutely. And to that end, we offer free Isaac Sim simulations. We can model your preferred robot, your preferred machine, and we can scale up the work cell to meet your demands, your production demands. So that's a free service we're offering. We hope to provide that for whoever needs it. And I think you're right that it really adds a lot of context, and it's really relatable. We can see these machines. A lot of our viewers here today, they know a CNC machine, they know the robot arm, even just the scene in this environment, it feels relatable. And that's helpful to scale up a problem, right? To sort of see your problem space in real life, well, close to real life, maybe.
So what led you to dive into this company, this endeavor?
Yeah. Well, I was employed and tasked with bringing in and onboarding robotics to a company that had never seen it before. A company that, in large part, the only automation being used was CNC, which at the time was so prolific that it was hardly even viewed as like automation as we think of it today. Right. But I was tasked with that, and I mentioned before, the second iteration of our first work cell was actually 1 robot, 2 machines, and I just wanted to see the robot work more of the time, right? The robot would load a part. In the 2 machine setup, it would be working more of the time, but in almost all the cells that we set up was 1 robot, 1 machine. The robot would load a part and then sit there for 5 minutes, like not doing anything. And I wanted to wear the robot out. I want to run the robot through so many miles that the drive in the joints just wears out. And that's what I want to get to. And I want to do that quickly, not abuse the robot, not give it things that it can't do or that are too hard. I just want to give it so many miles that it gets, we want to use it up. Right. That's where we want to get the usefulness out of it. So that led me to realize that if I could just get the robot to, reach, frankly, another machine, there was work to be done to figure out the logic, and it's complex to be sure, but here we are. We've arrived at a solution. So I've got, let's take a look at one of our deployments in the real world. And let me make sure that this is muted and everything. But we'll take a look at, this is a robot that we have installed at a local manufacturer. And this is MX interface running 2 machines. I'll increase the playback speed here just so it's not, we've all watched these videos and let them play out. So this is, as you can see, a static robot. It's just bolted in place in between the 2 machines. That means that it's almost always available. And what was our load time there? It was about 30 seconds. So, from here when it was standing up about to go pick up the part, that was about 30 seconds. So the important part here is that the robot's busy doing servicing machine on the left, and the machine on the right just finished its cycle, and the doors opened, and we will see the robot has recognized that after it has completed its work on the left machine, turns around and immediately goes to service the right machine. And don't mind me just shuffling the conveyor to make sure it gets the part there. And we actually did the robot in the background too. So this is actually an exciting line. This two machine cell farther down the line helped balance this line. This was the slowest process by far, and it was the bottleneck. But it's a pretty exciting moment when you can see the material flow from raw material 3-4 machines up the process, and then flow through and conveyor from one to the next, and come out the end a finished part.
It's the most exciting thing.
It is,
right?
yeah.
To do bakery and watch it go from like dough to bread. And it's a much longer process, but you could stand in the middle and look and see like, any part of the process of dough becoming bread.
Yeah, absolutely.
Well, I am curious, how can everyone work with you? Like what's the deal?
Well, the first step is reach out to us. Let us know what you're working on. Let us know the scale of your operations, and we'd love to jump in and help you figure out how to take advantage of that hidden capacity in your robot, or scale your operations up to multiple robots. So the first step is check out our website. You can find us at mxinterface.com. And take advantage of our free Isaac Sim simulation. We'd love to hear from prospective users about what machines they want to see, what robots they're using, and how they want to intermingle those. With MX Interface and its abstraction layer, we no longer have to make a homogeneous cell either. So even if you're considering a work cell that has multiple different machines that might have different capabilities, and there might be reasons to have that, or multiple different arms maybe that were purchased at different times, or different periods for different values, or whatever reasons that might be, we can get all those to talk together because we have the intermediate layer of MX Interface. So first step is reach out to us. Let's work together to build a simulation of your process, so that we can better understand where some of the constraints are, and then we can help develop that work cell, and we can provide the whole thing end to end. We can do end of arm tooling, we can do work holding design, we can make the cell complete for you.
Awesome. Where should people reach out to you? Is LinkedIn the best, or is email the best?
Yeah, you can find us on LinkedIn, both MX Interface and Process Robotics. Email works fine. info@processrobotics.com will get you there. Or myself, you can email me personally. I'm ted@processrobotics.com. So we'd love to hear from anyone. We'd love to interact with anyone about this.
All right, we'll put your contact info in the comments.
Yeah, sure, please.
I just did.
There you go. You're faster than me.
I'm
super laggy still. Thank you for doing that.
Oh, it displayed a little weird. Oops, I might need to do it again, but that's okay.
Yeah, we'll make sure the links are in the comments so you guys can email and go to the LinkedIn pages.
So one thing I do want to make sure I cover is the MT Connect agent going on that is helping to orchestrate this whole cell. I mentioned this a little bit earlier, and there is a small component called an MT Connect agent that is collecting and publishing all of the data from each adapter. Again, there's an adapter per machine. It's represented in what is known as an MT Connect agent. The page that we're looking at here is just a style sheet for the data the current data on the agent. And this is the reference implementation. So this would be available to any deployment that we do. What this means is that all of the data and time-stamped data is freely available to any user of MX Interface. It's all modeled in a hierarchical fashion, but what it does is presents the current data and further the sample data, and you could stream this. You can make simple GET requests to get this data. Maybe somebody wants to build a dashboard for their shop floor, and they want to show the current status of each machine. It's pretty trivial to do the GET request and publish that data, maybe display it on a screen, something like that. If you're from PLC land, you might be familiar with the term tags. So these are kind of like tags. The difference is that they are a little bit richer because they're rigidly defined by MT Connect. For example, here's Chuck's state of the machine number 1. Currently unavailable right here because we're not running a Chuck in Isaac Sim, but let's look at one that is. So the material handler load and unload requests, they're currently sitting at ready because there's no activity going on. But this is available, so this data can just be pulled from the agent as an MT Connect, in XML format, and then parsed down in whatever application you'd need to. Of course, we're available to help anyone do some further development, and we'd be happy to jump in and do that. But I just wanted to point out that the customer's data is the customer's data, and it's yours and it's freely available. If it's generated in your facility, it's accessible with MX Interface. So we don't want to hide this behind anything. It's all right here.
Right on. Thank you for adding that before we close out, because it's nice to know that you own your own data.
Yeah, of course.
You don't have to worry about it suddenly getting deleted or something.
Yeah.
You forgot to pay your license.
Yeah. Now, it is worth mentioning that this is a buffer. It's not a long-term data storage. So we can counsel customers and our connections on how to better store this in a long-term fashion. MT Connect agent is not really built it's not a database. This is a buffer of data. But because it's freely available, we can readily push that into a longer term storage. If you wanted to say, look back at last week or last month and how many load cycles machine X did, we can help customers do that too, if they want longer term storage.
All right. Right on.
Yeah. So that concludes the current development of what I've got. I just wanted to bring up one last video. I know we're coming up on time, but we've been developing this towards mobile robots as well. And we have this running. We have been working with Enabled Robotics to make sure that this is working with their mobile robot platforms. This is a quick demonstration. This robot is actually responding to those MT Connect and MX Interface tasks that we were talking about earlier. This is a pretty simple example. There's no machine involved here. It's just these crates over here. But this robot is reactive to and responding to the faux machines, if you will. So we're looking forward to developing this further, and we're looking for pilot opportunities for both the static robots, 7th axis robots, and the mobile robots. So if you're interested in that, please reach out to us, and we're excited to jump on that with you.
Excellent.
Yeah.
Well, thank you for a great demo today. This is, this mixes a lot of things that I'm interested in. So
Great. Well, happy to hear it. I hope to take better advantage of more robots and some of their possibly hidden capacity. And we want to see those robots utilized in more places and get better utilization out of it.
Right on. Well, you guys reach out to Automation Ladies or reach out to Ted if you got any further questions. And thank you very much for joining us today.
I appreciate
Bye.
the opportunity. Thanks a lot, guys.
Thank you.